What is a gradient function in vector calculus? In this video, I'll try to answer that question with respect to the material in Math 1072. Here I'll jump straight to the definition of what a gradient function is in n dimensions. First, you have a function f that maps from r to the n onto r to the n, where here n is any natural number not including 0, and it's essentially a vector function except for the case of n equals 1, where you take in a vector input and a vector output. And it is a gradient function specifically when there exists some secondary function here called the potential, v mapping from r to the n onto r, where f evaluated at every point v in its domain is equal to the gradient of this potential function v evaluated at little v. So for all v in, I could say domain of f, but I'm just going to say r to the n. You could replace this r to the n with the domain of f. The following question might come up a lot. Is this function f, given explicitly by the form f of x, y, z is equal to this vector, a gradient function with potential v equal to, in this case I'll pick out a specific example, x, y, z plus 1. The way you do this is simply by computing the gradient of v, the function potential that you're interested in, and seeing whether it equates to f at every point v. At every point in R3, sorry. So here the gradient of v is going to be the three terms, the partial with respect to x and with y and with z, but I don't feel like I need to reason my way through that. This is a fairly simple calculation, which is exactly the form of f as given up above. Hence, f of x, y, z, excuse my bad handwriting, is equal to the gradient of v. Hence, f is a gradient function by definition. Now we'll try to show a non-example of a gradient function. That is a function, a vector function, that is nice, that is continuous, but that isn't a gradient function. That is, there does not exist a function v, such that everything holds its gradients equal to f. And the way you could do this is by simply through contradiction. First, assume that f xy is equal to the gradient of v. We're trying to show that f cannot be expressed in this form, so one way to do that is assume it is, and then show that it leads to a contradiction. And this looks like this. This is going to be equal to the partial of v with respect to the first component, x, and with respect to the second component, y. Now you end up with these two simultaneous equations. And this might look intimidating at first, but you can tackle it in this way. First, you just start with the first term, the first line here. What does this show that v has to have a form of? Or at least, what does this imply? This implies that if you find an antiderivative with respect to x, it has to be of the form a half x squared. First, you have to have this to get this x here when you differentiate, and then add it on with a function of y, because when you differentiate it with respect to x, this evaluates to 0, this g of y. But if you differentiate this with respect to y, you get the form dv dy. The first term goes to 0, half x squared doesn't depend on y, but g of y completely depends on it, so you just end up with g prime of y. But this is equal to x, and this is problematic. How can you have that the derivative of a function only dependent on y depends on an independent variable, x? This cannot happen, hence you have a contradiction. Hence, f is indeed not a gradient function.